I'd like to thank you for coming this morning and the kind invitation to come and talk to you. And just to personally thank the European Association of Geochemistry that have funded this tour and got me. So I was in Krakow over the weekend, and then I'm going to Veszprém tomorrow, and then finally Bucharest at the end of the week. So I'm getting to go to a lot of exciting places that I haven't been to before and talk to lots of people. This is I think the main idea of this. So, and the office have just asked me to point out, particularly for PhD students, early career scientists, the opportunities. So there is funding that you can get from the European Association for Geochemistry, and also they have their own journal which provides access for publication for very short letters. So things that are just starting out. So I do encourage you to look at that. And also, as with everything, there is lots more information on the website. So what I'm going to do today is talk about the impact of volcanoes, a look back across them historically, see what we can learn about them from observations that we've seen going back a long way. We now have satellites, but we haven't had satellites for a particularly long time, certainly not on a volcanic scale. And we use this to predict the future going forward into climate models and things like that. And so we've already had my brief introduction. So I did the standard A-levels, so they're the high school examinations in the UK. So I did maths, physics and chemistry, and then I went through all the way to where I am now. And on the way, I've done quite a lot of work with aircraft. So this is our old Hercules aircraft, and we all have the glasses on because we were flying in the eclipse in 1999. So we flew out into the Atlantic, because during an eclipse it's like a chemical experiment. You can turn off the lights and see what happens with the atmospheric chemistry. You can't do that normally because the chemistry, the daylight increases in time. So that was like a laboratory experiment. That's me on board this aircraft here, and we're flying over the top. We are about 120 meters above that ship. The ship itself, we're about 80 kilometers south of the North Pole there. So we're looking at the effect of clouds in this region. This is the aircraft that I fly on these days. This aircraft no longer flies. The ship that you referred to is actually an airship, which is this. So 80 meters long. It was an airship that was flown across America as a part of a television program. And this is my most recent work. And that's where I've done most of my geochemistry, because I'm an atmospheric scientist, but I'm looking at the influence of what lands on the surface. But the people who are looking at the surface, they're the geochemists. So I'm learning a lot by talking to the geochemists. So, with big projects, you talk to people with lots and lots of different backgrounds. And that's the exciting thing that we can do. Not just always be talking to geochemists, talking to geochemists, but geochemists talking to atmospheric scientists and geologists and microbiologists and people like that. So when we talk about volcanoes, there are lots of different scales that we can think of. And perhaps the most important from how big an impact they have is actually the amount of explosive power. So without, as usual, there is a table of this sort of data. It gives some indications of what we call them. The plume heights, that's how high the material is thrown up into the atmosphere. So depending on where it goes in the atmosphere, if it only goes doesn't go very high in the atmosphere, it won't travel very far. But if you get the material all the way into the stratosphere, where there are high winds and there's a big global circulation, this material can stay there for a long time. So we're looking at the amount of material that's thrown up, and obviously as they become more and more explosive, the amount of material that's actually ejected during the eruption increases. And then there is a sort of classification in the same way that the epochs in time are classified. And just as an example, guidelines, how often these things happen, and finally some examples. And I'll be picking out some of these along the way as we're talking today, so some examples. So, and there are no doubt people in here who know a lot more about volcanoes and volcanic eruptions than me. So I do apologise if anything that I say is a bit basic. So with a volcano, we have a lot of different effects, and this image or this cartoon is based on the prevailing wind coming in this direction. So you can see that the ash cloud immediately starts blowing here, and depending on the size of the material that's ejected will help you predict how long it stays in the atmosphere. In the same way as you go to the beach and you pick up a handful of sand and throw it in the air with the wind behind you, the material that blows down the beach is the very, very small particles. The larger particles of sand will go down to the ground very, very quickly. So, and that's exactly what's happening here. So very close by, one of the big impacts for the population is volcanic bombs. And these are just big rocks thrown up in the air. They come down quite quickly, but they are significantly, that's a significant hazard very close to the volcano itself. There's a lot of material, there's slope damage, so you get a lot of material flowing down the slope from the volcano, and there's also lots of gases that are emitted during eruptions. And eruptions are all unique. You can't say that one eruption will be identical to the next eruption, even from the same volcano. So, and just a little bit of sort of data here on some of the major impacts, and this has just been on the local human population. So the Larky eruption in 1783, 9,000 people died, and we've got identifying how people, the impact of people. So Larky was just a lot of gas coming out generally. So there wasn't the impact of pyroclastic flows and things like that. The impact was the effect of the gases and the emissions going out into the atmosphere. Tambora, for example, again, a lot of because it was a large eruption, but it was very widespread impacts. So very widespread impacts means that they're not really going to be affected by, the pyroclastic flows. So this is where starvation was a major effect, and the same with Krakatoa. So the really big eruptions, they kill a lot of people very close by, but much further afield, that's where the big impacts are. So just before we get into volcanoes themselves, how many people have heard of the word albedo? Right, that makes it a little bit easier, because albedo is one of these words that a lot of people don't understand. They've not heard of it. When you explain it to them, they understand it. It's a very simple concept. So, as most with a lot of words in science, it comes from Latin, but basically it's a measure of how reflective the surface is. So, white snow, painting roofs, for example, to try and cool the environment is at this end, and then dark, fresh tarmac is at this end. And then there's a big range in between. And just to put a bit more detail on that, so very fresh, very low albedo, and albedo just goes from 0 to 1. It's very simple, make it very simple for us. So even asphalt will change its albedo as it ages. And then going through, we have vegetation, different trees have different albedos, bare soil, and that's dry soil. If soil is wet, it will be darker, which also means it absorbs more incoming solar radiation. It warms up quicker, water evaporates from it, and we get convective clouds. Desert sand, new concrete, open ice or ocean ice, and then fresh snow. And this is a lot of this information here, but we're also including clouds here. So clouds have changed the albedo of the planets. Clouds are very important if we're thinking about the colour or the albedo of the planet. So this is it's quite an old diagram now from the IPCC report, but it just emphasises the relationship between solar radiation aerosols and clouds. So this is material that's floating around in the atmosphere. And what we've got here is what's called the direct effect. So that's where solar radiation has a direct effect, or the aerosols in the atmosphere have a direct effect on the incoming solar radiation. So it can either be scattered back out to space, as we see with clouds. So this is high albedo. The light can pass through, or the light can also be absorbed. Black carbon, for example. Black carbon warms the atmosphere because it's dark and it absorbs incoming solar radiation. And then following from that, these are the indirect effects, and that's because aerosols will change cloud properties. They will change the size of cloud droplets, how long clouds last, and things like that. So these are all indirect effects, and these are all the sorts of things that we need to be putting into climate models these days, all these different effects. So just a very simple cartoon here. So this is the direct effect, solar radiation. So we've got aerosols, they can scatter or absorb solar radiation. This is how they interact. It's just like the theory of spectroscopy. So this is a scattering aerosol. So this could be clouds, it could be mineral dust in the atmosphere. This is a material that absorbs incoming solar radiation, so warms up. So this could be black carbon, for example. So that's how light interacts with the material that's floating around in the air. But we're just going to very quickly look at the local impacts. So these are the impacts that happen quite quickly following a volcanic eruption. And these are the ones that people generally tend to think of. These are the ones that people have a perception why their volcanoes are so dangerous. So we have lots and lots of different examples. So this is pyroclastic flow in Montserrat. So it rolls down the side of the hill. And this is a concrete block. And these are the steel bars that are inside concrete. So there's a lot of power going here. They've just been blown over like grass in the wind. We've also got, associated with the pyroclastic flow, are also hot gases, and hot gases, if you start breathing hot gases, you don't stay breathing for very long. So there are lots of famous examples in Vesuvius. And this is Saint-Pierre in Martinique, where a pyroclastic flow, that was a city of tens of thousands of people. The pyroclastic flow came down and it just literally flattened the city, wiped it out. Associated with pyroclastic flows, because there's lots of hot material here, is if you've got a mountain or a volcano, quite often because of the altitude, there is snow and ice. So you get the combination of snow, ice, and this hot material. So you get these huge streaming torrents that come down the side of the hill, and anything that's in their way just basically just gets destroyed. With the power of the eruption, lots of material gets thrown up into the air, and you see lots of different impacts here. So an instant one is just people being hit by this material, building collapse, power lines. So there's a big infrastructure impact following an eruption due to pyroclastic fall. Not quite as obvious, because an exploding volcano is very, very obvious. You can see it, you can quite often hear it. But also is the release of noxious gases. This is a lake in Cameroon, and there was a huge release of carbon dioxide from this lake. Carbon dioxide is heavier than air, so it sat there, and there was 1,700 people died in a matter of minutes. There are some quite famous images of just fields of cattle that have all just been killed by this. It wasn't an eruption, it was just a release. So now what they do is they actually pump water from the bottom out to the top, which just pulls out the carbon dioxide. So they have a management plan. They've worked out what it is. So the scientists went in, they looked, and they analysed what happened during the disaster, and they came up with a plan. So people can continue living there. So there is now a plan to prevent this from happening. Higher up in the atmosphere, when this material gets up, if it impacts aircraft, as we'll see later on, it can be quite catastrophic for aircraft. And this is the call sign of a British Airways 747 jumbo jet. And it was flying during it encountered a large volcanic ash cloud. And it was about 35,000 feet, and all 4 engines shut down. So, and in the way that pilots do, pilots are trained to do this. So he made this announcement. This is the name of the pilot, Eric Moody. So obviously the passengers on board knew something was wrong because there was flames coming out the engines, and then there was no noise because they'd turned all the engines off. So he said, "Ladies and gentlemen, this is your captain speaking. We are having a small problem. 4 engines on aircraft not working. That's a small problem is maybe an understatement." It says all 4 engines have stopped. We are doing our damnedest. We are doing our utmost to get them going again. I trust you're in not too much distress. That's the job of a captain, to keep people calm. Okay? And always remember that the captain is also on the aircraft that is falling out of the sky. So he wants to do that. He wants to get the engines going as well. And he did. He got the engines started, because if you turn it into such a steep dive, you start shaking the engines. And what happens is the volcanic ash, because most of it, they're glasses, so the glass which had impacted onto the engines and then cooled down, as they shook it, it shattered off. It shattered off sufficiently from the turbines that they could restart the engines. So, but you know, so this has happened a number of times, and this is why aircraft are particularly vulnerable to ash clouds. So going further afield, we want to think about the regional and climatic impacts, or the global impacts. So we have our volcano producing the ash cloud up to a certain height, maybe 10 kilometres. As we said, the heavy material falls out quickly. So when we're thinking about something in the environment, being it the ocean, in the land, or in the atmosphere, we think about how long something has as a lifetime. Most people are comfortable, a lot of people are comfortable with the idea of a half-life for radioactivity, but all chemicals have a lifetime. You know, chemicals such as chlorofluorocarbons have a very long lifetime, and that's why they last for such a long time and get all the way up to the stratosphere, where they can impact ozone. So different chemicals have different lifetimes, and it's down just to their reactivity. But anything in the atmosphere, one of the things that governs their lifetime is the size, the weight of the particle. So how quickly they fall out. So ash falls out of the, low down falls out of the atmosphere quite quickly. Also associated with these sorts of eruptions, we have gases, sulfur dioxide, for example, very quickly, because there's an awful lot of water that comes out of these eruptions as well. So very quickly it's turned into sulfuric acid and aerosols, so sulfur, we call this sulfate aerosol. And depending on where it gets to in the atmosphere will once again govern its lifetime. So the higher up it goes, the longer it lasts. And then tied to this is that this is all producing aerosols that are stopping the solar radiation. So then there's a heating effect up here potentially, but underneath there can be a cooling effect. So we've got to think about these, the repercussions, the after effects of these explosions. So we can have lots of volcanic ash up into the atmosphere producing sulfate aerosol. We're changing the albedo. If they get up to the stratosphere, there can also be an impact on ozone. Volcanoes will also produce greenhouse gases, things such as carbon dioxide, and that's not normally a problem because normally they're quite small compared to how much carbon dioxide we're producing. They can last for a long time depending on how high they get up in the atmosphere. And also, as we've seen, aerosols will affect clouds. So we potentially get changing rainfall patterns. Changing rainfall patterns over a long time, over a year, could affect crops, which then affects the local population. So the volcanoes themselves can impact the ozone layer, and this has been seen because we now have sufficient observational capability through satellites to actually see this happening. And it's the particles themselves that are interacting in the stratosphere. So in different regions of the atmosphere, different compositional elements that are produced by the volcano will have different impacts. So we have to think about what we're producing and where is it actually going to. Now, one thing that volcanoes has helped us is to understand the concept of global dimming. Now, most people, non-scientists are comfortable with the idea of global warming, but we also have a concept of global dimming. So has anybody heard of global dimming? So it's quite a simple concept to understand. It's just not one that people talk about because it's all about everything getting warm. So increases in concentrations of sulfur dioxide produce sulfate aerosol. The sulfur dioxide dissolves into water, producing sulfuric acid and sulfate aerosol. And that has a net cooling effect on the atmosphere because it's just producing an aerosol which is reflecting out incoming solar radiation. And we've seen that from big volcanic eruptions simply because they produce so much. We can see that signal because if you're studying the environment, one problem is there's lots of different elements that might be affecting the environment. So to have conclusive proof or to be very confident of one element in particular affecting the environment, you have to increase the volume of that element, so to speak. So we're much more comfortable and confident about the idea of global dimming now because we've had volcanic eruptions such as Pinatubo in 1991 that have produced so much sulfate aerosol, we can see a very clear signal from various different factors, temperature, stratospheric aerosol optical thickness as well. So, and global dimming happened for about 30 years, up until about the mid-80s, and that's as people with the Industrial Revolution with burning, or the stage of the Industrial Revolution we were at, was we were producing so much sulfur dioxide from burning coal. And what was happening was that sulfur dioxide was producing sulfate aerosol, and that, to a certain extent, was reducing the impact of anthropogenic gases such as carbon dioxide, which warmed the atmosphere, and the sulfate aerosol cooled the atmosphere. But the reason for removing sulfur dioxide from the atmosphere was nothing to do with global dimming. It was something else. So in the UK, a lot of our power plants were burning coal, and the coal was producing sulfur dioxide. The sulfur dioxide would blow to Scandinavia in the wind, and there it would rain out as acid rain. So we'd see the repercussions of the sulfur dioxide as acid rain, so all the forests were dying out in Scandinavia. So at that point, we said we have to remove or reduce the amount of sulfur dioxide. We have to install desulfurization plants on our power stations to protect against acid rain. And when we did that, then it was noted that the warming temperatures started to pick up and started to accelerate because we no longer had this cooling channel. So this was a repercussion of acid rain. It wasn't because we knew about the idea of global dimming. People had an idea about it, but until we had Pinatubo, we didn't know for sure. But we can understand this now. So one advantage with our huge eruptions, such as Pinatubo, is they teach us a lot about the atmosphere because they are huge experiments. So we simply cannot, and maybe should not, be thinking about doing because we don't know the implications of them. If nature does it, we have no control over it. So just to put some more information onto Pinatubo, Mount Pinatubo in the Philippines, 1991, 20 million tons of sulfur compounds into the sky. So a huge eruption, enormous eruption. And this could be, so now we have satellite imagery, so we can see this is the location of the volcano itself, and we can see the plume coming out. This is the major plume, and an hour later, so we can see it growing. So this is a big and quite a fast eruption, and you can see it spreading out there. So this is a significant amount, because this is 100 kilometres across. So this plume here is 500 kilometres across, something like that. And I don't know what city from here is 500 kilometres away, but you know, just as a scale, just look on Google Maps and see how big that is. That's an enormous area. Lots of close impacts. If you can see that much material over 500 kilometres from space, imagine what it's like underneath. So these are buildings sticking up, and this is just ash that has fallen down on the local population. And then other people could see it. So this is a photograph taken by one of the astronauts in the space shuttle. So this is 15 kilometres. This is the aerosol layer above. So very quickly it spreads out very quickly, and you can see it. So that, you know, it's when you can start seeing them with the human eye from space. That's a big signal. Again, satellite images. So this is Eötvös. This is 9 years earlier. And think about how good satellites are now. So these images were collected before most of the people in this room were probably born, I think I could say. I just finished my first degree when this happened. So, you know, this is quite basic satellite imagery. It's nothing compared to what we can do now. But you can see that this is a significant amount. This is sulfur dioxide from the TOMS satellite. So when these things start happening, then people start going back and looking at data. Can we see this signal? Because there's some enormous event happened here. So this is Eötvös and the Pinatubo eruptions, and this is just the temperature. So it's pretty clear there that we can see there's a significant drop. There's also other drops, but we can start tying together why these have happened, how fast the heating recovers. That also gives us some confidence, because we can put it into climate models. This is the temperature profile, so we can see the average is still increasing, but it's possibly just slowed it down. It's just pulled it back a little bit. So one thing that we can do now we have these observations is actually to try and model it. So we put the information we have into climate models. So this is a global climate model. These are two different sets of observations. And we can see that our models and reality are pretty good. So at that point, we're thinking that the science, the maths, the physics, the chemistry in our models are pretty good. There's always room for improvement to increase the sophistication of our models, but this is showing that our understanding is getting quite good of how these systems work. So we can go back and have a look at a variety of different models. So that's just having a look at the climate model that's producing temperature. So now we're putting in things like the radiative forces, so greenhouse gases. There's a nice continuous increase in the greenhouse gases. And these are the radiative forcings on different components. So stratospheric ozone reduces the forcing, but there's a significant impact here of stratospheric aerosols, and they're tied exactly to the dates of these eruptions. We can look at the surface temperature driven by these different factors. So we can, in a climate model or any model, you can basically turn different things on and off. So you can see the effect of them just to do a sensitivity. And that's one thing that we do to help our understanding of it, see how important something is to be measuring. And then we can look at the impact on the surface. So again, these are the two eruptions. This is where they're happening. And what's happening now is, So this is light arriving at the surface, and this is people thinking about crops now. How does it impact the crops? Because the crops, you know, they need light, they need photons for photosynthesis. So what we've got now is this is the direct light arriving at the surface, and that's gone down, as you'd expect. It's been turned off. But actually the diffuse light has gone up, and the diffuse light is in exactly the same way as if you're driving a car on a dark night and it's very misty. If you turn the headlights on, the mist reflects back. So that's the diffuse lights. That's what we're seeing here. And crops do respond to diffuse light, but it's still reduced amount of solar intensity. So it's not catastrophic because there is this diffuse light, but it's not all the right wavelengths that the crops want. So, and looking at this data and then looking at these are the global yields for the 4 staple crops that we grow on the planet: wheat, rice, maize and soy. And you can see it's not quite so clear for the Algecion eruption, but certainly for the Pinatubo eruption, and this is the stratospheric aerosol optical depth, so there's more material in the atmosphere. This is just so we can line this up. We can see that all the staple crops have actually reduced in yield. So long term, there is a significant impact on crops. And this is I think maize was something like 8 or 9% yield was down, which is, it doesn't sound like a lot, but that's a lot of food that you are not growing, you're not producing for people. And then we use Pinatubo as a great way of testing all our different understandings. So we go, you know, so the ozone scientists were looking at the effect of Pinatubo. They simulated Pinatubo in their models and see how it affected, and we can see that the ozone did have a significant, so this is all dropping because of CFCs and starting to sort of kick back after the Montreal Protocol. But this big drop here is associated with the effect of Pinatubo in the stratosphere. It does recover because these materials don't stay, they don't have the lifetime of CFCs, so it recovers a lot quicker. So the impact isn't as long. And then going back in time, so Pinatubo, we have satellites, we have lots of different chemical analysis. People could fly balloons, they could fly aircraft through. But in Krakatoa, and going further back in time, we're reliant on lots of word of mouth, people's drawings, paintings of this. So Krakatoa in 1883, it was a fairly violent eruption, and so I have very little geology, but this is the subduction of the Australian plate underneath the Eurasian plate. That probably means a lot more to people in this room than it does to me. So, and this is the chain where there's been an awful lot of eruptions. We'll come back to Tambora later on. But there's just a huge line of volcanoes, and you can see that these were produced by just eruptions over time. So, and there was multiple different stages of the Krakatoa eruption. It started with an earthquake, so that's the thing that sort of destabilised the whole system. And the first explosions were heard 160 kilometres away, which is quite a long way. If you hear an explosion 160 kilometres away, that's quite a long way. But that was quite a small explosion compared to what came later. And when they say August 26, several loud eruptions, I don't know what a loud eruption is compared to something you can hear at 160 kilometres. So masses of material being thrown up a long way into the atmosphere. And the last of the eruptions was the largest can be heard from Sri Lanka to Australia. So we've gone from 160 kilometres, which is quite a loud bang, to 4,600 kilometres. That's a very, very loud bang. And I think they've said that it's the loudest noise ever recorded. So, which is that's a fact that I like. Loudest noise ever. So, and this is what happened after the eruption. So basically, so much material was thrown up into the sky. An island disappeared, which is quite commonplace with volcanoes. So, and you know, the volcanoes, just to understand just how much energy is associated with this. And this is the one that you've got all these different facts. You've got tsunami, but barometers measuring pressure around the world detected shock waves that went around the world 7 times. So that's if you can detect that, and that's in 1883. This is not a very sensitive barometer that you know people have in a physics laboratory. This is fairly rudimentary instrumentation, and they could hear. So you could sense this pressure wave go around 7 times. And needless to say that the dust and ash, because it got so high, there's so much energy associated with it, it's encircled the globe. And there's lots of theories about the impact, and a lot of people, and it's exactly the right time, say that the painting, The Scream by Edvard Munch, that sky is due to Krakatoa. So, you know, the artist looks up, he sees these vivid colours in the sky, it goes into their head. So next time they're painting, and it's not just one, so again, I think the same influence is happening here and here. So it may just be a coincidence, but this fits with exactly the right time for the Krakatoa eruption. So it's not just scientists looking at the sky, it's people seeing this. And then I noticed this quite recently. We have lots of new satellites, so there's lots of Sentinel satellites being launched at the moment. So this is from this year, and this is actually a plume from Krakatoa itself. So Krakatoa hasn't gone to bed. It's still detectable, and we've got very, very highly sensitive sensors on board this. So this is a Trompy on the Sentinel-5 platform. This is Krakatoa itself, so basically it's just let out a plume that's just floated across out into the ocean. Krakatoa itself is just there. So it's still there. Then going back a little bit further in time, Tambora. So, and this one's known as the year without a summer. So, and that's a global summer. That's how big the impact was. Back on the same archipelago as we've seen, this was a bigger eruption, another order of magnitude bigger than Krakatoa. And lots of people like to go back and think just how big was it? So it's the biggest one for about 2,000 years. So, and just some of the facts associated with it. So masses of material thrown up into the sky. 10,000 people died very, very quickly just from material falling out of the sky on top of them. And then because of the impact on water and food chains, so crops failed, animals couldn't eat. So then the big impact is down to starvation because of disruption of the food chains. So the whole normal growing season was impacted quite significantly, and it's been estimated because a lot of people, there's quite a lot of information in there, proxy data that we can use, and people just running models as a simulation, and it's thought that the global temperature dropped by 3 degrees over this time. The impact all the way around across to America, because suddenly if America is impacted, then they start caring about it. But there was widespread snowfall, basically the snow at the wrong time of year. So people start thinking, why is it snowing here? And then they look further afield for the effect of that. You can also look back in the records for different materials, global transport volcanic markers, so you can look at different metals. You get a lot of mercury out of volcanoes, for instance. So, and if we track back, look at the amount of mercury that you can get from cores. So these are cores of glaciers in Wyoming. They tie fantastically well with volcanic eruptions. The background here is increasing through the Industrial Revolution. We've got the gold rush actually releasing more mercury into the air, and then it's circulated round. So all these different features, or nearly all of them, we've got some things that we're not quite sure of still, we can explain these. So we look at a long time series of different events and we can tie them all together. So this is where our theories start to make sense as we go on and on and on, and we see these correlations between an event and an observation, potentially a long way away. This is thousands of kilometres away, but we are seeing the influence of things like Krakatoa and Tambora. Again, artists always looking at the sky, and if the sky changes, they'll incorporate it into their paintings. So this is J.M. Turner, and yellow skies aren't particularly common in the UK. So certainly worthy of mentioning. And also, it's thought that because the amount of sunlight was reduced, we call it, as I said, the year without summer, that made people just be more melancholy and sad. So one theory is that the idea of Frankenstein was concocted during these melancholic periods. So sort of makes sense, but I don't know. That's call me a little bit of a cynic with that one. But there's stories that people like to put out there. So one thing I mentioned earlier on was Larky. So Larky was not a volcanic eruption in the traditional sense. So it's another nice test for our computer models. So there's been a lot of computer modelling done on this. This was in Iceland in 1783. And this was a fissure reaction, eruption. So a long chain just started to produce gas, sulfur dioxide. That's where it's located, where most of the major volcanoes in Iceland are. The land of fire and ice down here. And so this is the fissure itself, and it produced 580 square kilometres of lava. So there's an awful lot of material came out of it. So this is where we got the timeline. 60 teragrams of sulfur, that's a lot of sulfur going up into the atmosphere. And over half of that was released in the first 6 weeks. And knowing these sorts of facts helps us to actually put them into computer models. It's not all going out in 100% in the first day. So it means that we can slowly artificially contaminate our environment for our model, if you like. Reached the tropopause, we had this dry fog. So that's because of the very acidic nature of what's coming out of this. And the temperatures fell to nearly 5 degrees below the running average for the region. Fire fountains, like with most volcanic things, very, very spectacular. People love to go and look at these. Now, one thing that people did start looking at was the actual effect on the local population in Iceland. So you've got this very rapid dip here. So this is not all the way down to the bottom. This is 48,000 people to 40,000 people. So 20% of people in Iceland died from that. Now, that doesn't sound, that's a big number, but it's 8,000 people. 8,000 people out of 50,000 people is a lot of people. You know, that's and especially depend on who they are. If they're young children, then there's a sudden dip in the population, you know, going forward. So these suddenly become, there is a recovery in the birth rate, which actually does have an impact as time goes on. So one thing that we try and do is actually work out how much sulfur dioxide was erupted. So people always want an analogy. So the analogy is how much sulfur dioxide is produced in the UK. So in the UK, this is millions of tons of sulfur dioxide. I can't remember what year this is from. I think this is post default sulfurization times. So that's each year. Now, just notice that this will drop down. So before we brought in the Clean Air Act in the UK, we used to have very, very bad, they were called pea soup because the fog was so thick. So this is much more higher levels of sulfur dioxide in the UK, and that's where people, they used to have to have torches in front of cars during the day because you couldn't see far enough. And then just to compare that, that's the Larky eruption. So we could see that they're quite significant, but the Larky eruption produced absolutely masses, just an unimaginable amount of carbon dioxide for such an event. The plume circulated the globe, so we got this all the way across Europe, Russia, North America. There was crop failure across Europe, so we're seeing this signature of the eruption quite a long way away. It's reported in newspapers, so when people start talking about it in the street, in newspapers and things like that, then it's, you know, it's becoming a big thing. If we were talking about it, it wouldn't need to be, you know, because we're thinking about the science and the impact, but if people in the street are stopping talking about the weather or the football to talk about a volcanic eruption, you know, something quite seriously is happening. So this is the increase in UK mortality. So this is much further afield from Iceland. So the first haze was observed, and this is during the eruption because it's quite a long, drawn-out eruption. So we're seeing an increase in the mortality associated with that, and the papers are actually reporting it. Now, 186 doesn't sound like many, but if they're reporting it, it's a statistically significant number for people to start thinking about it. Models have looked at the temperature anomaly, and this is based on a 31-year mean. But actually, if you wind the mean back, make a much longer contributing mean, 225, this is where it was about almost 5 degrees lower in temperature. And you think about the impact on the planet of an increase in temperature of 1 degree that's happened since pre-industrial time. That's turning it right back very, very quickly. And the issue about this is it changes it very, very quickly. There's no response time. So the environment doesn't have so it has a cataclysmic effect. So they've done forward modelling into the future. So if there was a Larky type eruption in the future, you can see that this is the effect. Obviously, the closer you are to the eruption, the bigger the effect. So there's a significant number of premature deaths associated with a Larky style eruption in the future. Now, more recently, there was the Bardabunga fissure in 2014. So at that point, because we have lots and lots of instrumentation available to us, we go out and make lots of measurements and start looking at that and running models so we can compare that. So our instrumentation is getting much, much more sensitive. So that's where we can actually detect increases in sulfur dioxide nearly 3,000 kilometres away. And that's not necessarily because it's much higher in concentration. We're just much better at measuring it these days. And we can look at, this is a computer model showing the release of sulfur dioxide gas and then converting it into sulfuric aerosol. So you can see these, it's not a continuous emission, it's just like plumes, big release and then a reduced release. And you can see the circulation patterns are just rotating it around. We're building up the background concentration because these concentrations just staying up. This is much longer lived in the atmosphere because this reacts to produce this sort of material going forward into the atmosphere. This simulation is just run for a month, so we're about halfway through the month there. You can see there are just continual emissions there. Colour is obviously on the strength of the emissions. You can see that we've got changing weather patterns as you'd expect, and generating these quite concentrated filaments coming down and then sweeping out across Europe. So with our computer models, we can look at these and compare them to measurements on the ground. So we've got fantastic capabilities now. And just remembering that that was a tenth of the size of Larky. So I think it won't be long before we'll be able to start seeing the actual regional effects of this eruption. We're already looking for the signals. So, and one of the most recent eruptions that highlighted it, certainly in the UK, although there's very few people in the UK that can spell the name of the volcano. I'm one of them, I can't. So I work with an Icelandic scientist, and she can pronounce it, and it's what she does. So I will not try to pronounce it unless anybody else can. Anybody willing to try? Apparently they call it E15 for the people who can't pronounce it. So, or just the Icelandic volcano. So 15th of April 2010, there was an eruption. So it's based here and it's spread out. So this is basically a composite for 10 days from the Volcanic Ash Advisory Centre. So there's a network of these around the globe. They all talk to each other and they feed their data into each other's models. So you can see the impact. It's spread round a long, long way. So, and the initial concern was actually that aircraft can't fly. And if you start aircraft can't fly, maybe one day, that's okay. But it went on and on and on. And at this point, because there's, you know, if your aircraft can't fly, aircraft on the ground is just costing money. They only make any money if they're in the air. So the amount of money that people were starting to lose was getting significant. People couldn't go on holiday. And when the people can't go on holiday, that's the government's fault. So one thing that we're much better at now, but we're not very good at, is actually being able to model ash in the atmosphere. Because they say, oh, there's been a volcanic eruption, nobody flies anywhere near it. Whereas actually, what you need to do is understand the different layers, and the atmosphere is three-dimensional. So you could fly around it. You could, if it's at a certain level, if you can get above it and stay above it, you're safe. You're away from it. So these sorts of things were popping up around the country, and that one problem was that people in other places around the world, flights weren't happening because the aircraft they were originally supposed to fly on were stuck. So suddenly the repercussions, the ripples out of these aircraft not flying, goes out across the planet. So the number of flights that were cancelled, and this is hundreds of thousands of flights. The impact to the UK economy was £500 million. And it was probably 10 times that on the global economy. So you can see that governments have suddenly started thinking we need to understand these more. We need to understand how we can mitigate for them, or how we can mitigate the transport for them. Now, thankfully, you can get permission to fly on them in an aircraft if you've got an aircraft that measures volcanic ash. Normal aircraft do not measure volcanic ash. So this is an aircraft that's equipped with a variety of different sensors. So this is a sensor that measures actually the dust. in the atmosphere. So it means that if the pilot's flying towards the volcanic ash, there's information in flight so that they know what the concentration is they're exposed to. So if the concentration goes up too high, they can turn around and come back because they are actually making that measurement. They're measuring it, thinking about the albedo all the way back, because the ash scatters light. So if you can measure how much light is being scattered in a certain volume of air, you can work out how much ash is there. So we use what's called an optical particle counter, and that will tell you how much material you're flying through. You can always look out the window, but generally if you look out the window and you can see it, you're probably already in it. So this is a different aircraft, but this is the layer sitting on top of the clouds. There were a number of different flights because they're trying to fly into the plume and then comparing the measurements they get to the atmospheric models. Because it's ultimately, if you have another eruption, you're going to look at the atmospheric model, and that's going to define where you close your different air corridors. So that's what's happening here. So this is, each colour is a different flight. So we're just mapping out the atmosphere. We can use what's called a LiDAR. So this is basically just a laser looking down, and it measures light being scattered back. This is the ash cloud itself. We're flying over the top of it. So this is the aircraft flying along here. So this is time looking down. So these numbers here are related to these numbers. So this is where the ash cloud is. The rest of the yellow is the flight track, but that's flying over the top of the ash cloud. So we can see that because light is being scattered back, and we're measuring it with the LiDAR. Again, this is same instrument, different data set. So we can look at the polarization, so we can see the difference between particles that polarize the light, such as ash, and sulfuric acid, which doesn't. So we can see the difference here. So we can discriminate between which is ash and which is the sulfuric acid. We can do exactly the same from the ground. So these are instruments that are flown on satellites. You can put them on the ground, you can put them on the aircraft. So this is again a timeline. And this is a single instrument at the same place. And this is the ash cloud passing over the top. This is down in the south of the UK. This is the ash cloud as it passes over a site in the Netherlands. So we can see the progression of this ash cloud across. So we can look at in situ measurements, we can look at measurements from satellites, and we can compare them to the models. So this helps us to improve our understanding of the models and whether the models are any good. This is the ash cloud itself, and you can see that all the airlines were flying south, avoiding it, and then, so people could get as far as Spain into southern France, but they couldn't get any further, so the aircraft was still operating. So then finally what I'm going to do is just go back a long time. So this is Toba, about 75,000 years ago. And this, you probably guessed, if we're going to talk about something that happened 75,000 years ago, this is going to be a big eruption. So just for a change, we're in exactly the same region of the planet. This is Sumatra again. So we have, this is the island itself, and this is, remember, this subduction zone. And just to remind you, this is Aceh. So does anybody remember Aceh? So that's the tsunami, Boxing Day tsunami in 2004. So there was I think it was, the earthquake was, I think, 9.1 on the Richter scale. And this is this enormous tsunami that taught lots of people about exactly what a tsunami is. So we're seeing that we've got lots of volcanoes going off, but this is a very active region tectonically. So, and the explosion itself, when you think about Tambora, the year without a summer, we talk about Toba, they refer to it as dwarfing Tambora and Krakatoa. Krakatoa, the loudest recorded sound ever, went round the planet 7 times. Toba dwarfed this. So it blew a hole lump out of the ground, up into the atmosphere. Nearly 3,000 square kilometres of solid rock was ejected 30 kilometres into the atmosphere. This was an absolutely phenomenal eruption. And they've gone back looking at the records, and because the temperature dropped so much, I mean, this was almost the end of the human race. This was almost our 65 million year asteroid, because it's been calculated that the population dropped to less than 10,000 human beings on the planet following one eruption. So that was just demonstrating just how powerful these things are that we don't have any control over. So just to summarise, we've shown local impacts. You know, generally there's quite relatively small numbers of people. You know, rocks falling from the sky, roof collapse, things like that. And then regionally, you can have lots of crop failures, things like that, because of the sulfuric acid that's going out, something like Larky. Globally, thinking about tempora, because we basically just dialed back the sunshine, and that has a climatic impact all over the globe. But volcanoes are fantastic because they teach us lots of things. They prove lots of theories. You know, people are, you know, they've got these lots of ideas, and these computer models are showing something, or their measurements are showing something. But sometimes you can't have the confidence in them until we have something like one of these enormous eruptions, because the signal there is so big it can't be anything else. So that's just summarising. But finally, I'd just like to acknowledge, you know, you guys for listening to me today, the European Association of Geochemistry for bringing me out to Budapest this morning, and my two colleagues, the two volcanologists that are genuine volcanologists. So Evgenia and Anya, who is just talking to them. You can see the enthusiasm, because people who work with volcanoes, they go to fantastic places and they're always really, really excited. So just talking to them, you want to be a volcanologist. So, and with that, I'd like to thank you, and I'm happy to take questions.